Thank you very much for this kind invitation. Well, mechanical ventilation has been rather elusive. It's been something that's really been extremely difficult for me for the last 20 odd years, and I'm still learning the way we should ventilate our patients well. And definitely it is going to be this lecture, this place, this conference that is going to help you out, especially because all of us leaving this hall at the end of the day, leaving the workshop, will probably learn a lot at the end of this day. And to help us, there are a lot of faculty, a lot of senior faculty who will probably help us hold our hands and take it to that level. But the important thing, as Dr. Anila Malde said, Madam, you said that it's important to ask questions. And I think that's the ultimate objective when we have a workshop. People should ask questions and they should clear their complete doubts. And many people don't ask questions primarily for the primary reason they feel that they're stupid. They sound stupid, but it's not that way. The smartest people on the planet are the ones that ask the most questions, right? So with this, we must understand that even small questions are responsible for actually creating discoveries. Okay, creating discoveries. And it is these discoveries that go ahead and make it advances. And today I'm here to talk to you about some advanced modes of mechanical ventilation. And slides are available on drsanjith.com. You can easily go and have a look at it. There are two forces that are responsible for advances. And the first force is the unending medical research that comes in. This medical research actually gives us so much of data points, that at the end of the day we have too much to learn. And the second force is the industry. Unending products, unending ways, unending equipment that comes in and creates more amount of complexities in care. But importantly, they all help to do one thing. They all help to save lives. So at the end of the day, advances are not something that you say, I don't need. It may be used rightly to save lives. But importantly, if you don't ventilate patients well, the basics, if it's not done well, ventilation can kill. It's very important for you to understand this. It can kill. Well, what exactly do we want these machines for? We want these machines for to do few things. The first thing that we want to do is we want them to oxygenate and ventilate. Very simple. I would be happy if it was automated and safe, if it's automated and safe. And we learned in COVID, when we had less people, automation is the one that actually helped us. Okay. The third thing is comfort. I want my patient to wake up in the morning like a daisy. And that will occur only when the ventilator is very comfortable for this particular patient. The third thing is I want to reduce the work of breathing. And importantly, I want the ventilator to work in such a way that I can easily liberate this patient from this particular device. So if I have all of these ideally done on a ventilator, I think probably we may be probably jobless. Dr. Aparna has clearly talked about volume control, pressure control, SIME and pressure support, and these are our workhorses. But they give us an insight as to how advanced modes work. And if you ask me, what are the advanced modes? There's so much of advanced modes, so much, that it is beyond the scope of this lecture to talk about each and every one of them. So what I'm going to do is, I'm really going to talk to you just about the basics of each of these modes, the basics, all right? I will break down this ventilation in such a way, and I'll explain to you the key points as to why and what these particular modes do. Well, the advances are on three key areas. The first key area is the fact that it guarantees a certain pressure and a certain volume. This is what the first key area that we look at. The second one, it helps us to move from phase to phase to phase, right from start till the end. So this is the next advance that comes in. That means you are at high pressure, you're at low pressure, you're at high compliance, or at low compliance. All over the time, this ventilator adjusts, and it takes you through the entire process of being started on the ventilator to being liberated to the ventilator. And the third important advance is microcomputer technology. This technology is the one that has opened up comfortable ventilation. So with respect to that, the first kind of ventilators that I used were the open loop systems. And I was here when we used the Manley. We did use the Manley. The Manley was a system that it was a glorified ambu bag. So what happened over there was you gave a certain order, the ventilator did what it wanted to do, and it didn't look at the patient. This is the open loop system. All right. There was a lot of benefits on that. It is very, very cheap, actually. It's very, very cheap. But however, the patient has a very, very tough time coping up with that kind of ventilator. Well, now what has happened is we've come up to closed loop systems. Okay, now in the closed loop system, there is a feedback that comes from the patient, which goes to the device, or goes to the controller or the clinician, which then controls the ventilator again. This is the closed loop system, and that's what the advance is all about. So what are these closed loop systems? I mean, you're using closed loop actually. If you look at it, when you go and dial an FiO2, what's happening over there? You're giving the FiO2 at 40%. The ventilator is actually taking and making that as 40%, and throughout the time it is keeping at 40%. That's a closed loop. It's a device closed loop. Now, if this patient gives back a feedback to the machine, if the patient gives a feedback to the machine, that becomes a physiological closed loop. So you have a physical variable of the device, like an FiO2, and you have a physiological variable of the patient. For example, when Dr. Aparna talked about pressure control. Now in pressure control, what is happening? You're setting a pressure, and then the device all over the time starts maintaining that pressure in the body because it gets a feedback from the patient. That's physiological variable of the patient, right? Now let me tell you, the entire closed loop system has become so popular because of the fact that physiological closed loop control has proven to be much more comfortable, much more easier, and this was very well elucidated during the COVID pandemic. Alright, and the entire focus of closed loop ventilation is actually the patient. Okay, the focus is the patient. A physiological measurement comes back from the patient to the controller, and in this case, in this closed loop system, the controller is the clinician. Then the clinician takes the call as to what I should be doing with the tidal volume, what I should be doing with the pressures, what I should be doing with what I'm doing with the rates and stuff like that, and then alters the ventilator settings. This is the actual physiological closed loop system with the physician inside the loop. So it's an inline closed loop system with a physician inside the loop. Of course, this is time consuming, this is labor intensive, and it needs the full attention of the clinician when you do something like this. What's gone ahead is we've eliminated the clinician from this loop and taken him out, putting a physiological measurement in place. Which controls the ventilator. So let's look at it. Okay, let's take the example of a simple closed loop system called as a smart care, where you have ETCO2 over here. So I changed the ETCO2 and I told the ventilator you need to keep the ETCO2 at 40. Alright. So accordingly what happens over here is the minute ventilation changes as per what I have set. Now what happens during the entire process, there is a change in the minute ventilation that occurs and a change in the ETCO2 that occurs. When the change in the ETCO2 occurs, the monitor now and the ventilator now understands that there is a change in the ETCO2 and then again changes the minute ventilation. This is an example of a physiological closed loop system. And there are many of these physiological measurements that are taken into content to actually make these systems. Some of them will look at protective ventilation, ventilating them between tidal volumes that we want them to ventilate at a certain pressure. Some of them will look at carbon dioxide like I just now showed. Some of them will look at oxygen like it looks the PEEP in the FiO2 tables. And some will be a demand controller. So there are various types of closed loop systems. So the era of physiological closed loop feedback control is definitely here. And now let me go ahead and talk to you a little bit about the advanced modes in short. Alright. So the first mode I'll talk to you is about PRVC, and I try to cut it short and make it very simple for you. Alright. So PRVC is also called as pressure regulated volume control. It's a dual control kind of situation where it delivers a set tidal volume at a minimum pressure. This is the line that actually defines PRVC. It delivers a set tidal volume at the minimum pressure. How does it do that? When it gives a test breath, after it gives a test breath, it compares it to the set tidal volume that I have set. Alright, and then what happens is, it looks whether the tidal volume that I have set is equal to the delivered tidal volume. If that occurs, then it continues at the same pressure all the time. Okay, so I've got my guaranteed tidal volume at the pressure that I want to. Now what happens in the case that the tidal volume that the ventilator has delivered is not equal to the set pressure? Then it increases or decreases the pressure, increase or decrease the pressure as per what I have set, as per the controls that I have set, and thus go ahead and ventilates this patient. So it's a physiological closed loop system where it changes the pressure as per what I want to a certain guaranteed tidal volume that I have set. But there are limitations. Now what are the limitations? So if the patient demand increases, that means the patient effort is increasing, right? If the patient's effort is increasing, that means that actually the ventilator should give more support. But what happens with this ventilator is, the moment the patient demand increases and the effort increases, the volume is increasing. Okay, when the volume increases, the entire ventilator feels, oh, the volume is getting higher and higher. Let me reduce the support. and it actually reduces the support. Okay, so this can be counterproductive. Okay, this is something that can occur in PRVC mode. Well, let's look at another mode called as volume support, sometimes called as volume assured pressure support, and taxonomy has always been a problem in ventilation. So what does this do? This guarantees a tidal volume at a preset minute ventilation by varying pressure support. Till now we didn't put pressure support in the equation, now we're putting pressure support into the equation. How does this do this? Well, there's a trigger. Now this trigger is a pressure supported test breath. The compliance is determined and the pressure limit is fixed. Then the flow reaches 5% of peak flow. When the flow reaches 5% of peak flow, it now compares the volume delivered versus the volume desired. Okay, so once it compares the volume delivered versus volume desired, if it is equivalent, then what happens is it goes back to that same pressure and continues the volume support. So it gives you guaranteed tidal volume at the pressure. Now what if the volume desired is not equal to the volume that is delivered? Then a new pressure set is achieved to achieve that kind of tidal volume. And then the pressure is fixed and the ventilator keeps on ventilating. So this is volume support, something like a PRVC but in a support mode of ventilation. Let's take the example. Okay, you have a patient, you set a frequency of 10 per minute. Okay, you have set a tidal volume of 550. That means I'm giving a minute ventilation, I'm set at 5.5 liters, tidal volume into RR. Now, let's do one thing. The patient breathes only 7 per minute. Now, if you're going to breathe 7 per minute and I want to give 5.5 liters per minute, what it does it need to do? Because I've told them to guarantee a minute ventilation. I've told them to guarantee a minute ventilation. It actually increases the tidal volume to 150% of up to 150% of what is required. And so the next tidal volume will become 790. You understand? So with this, it is actually guaranteeing my minute ventilation. But what is the problem? The problem is if there is fever, if there is acidosis, there will be an increase in the effort to breathe. Okay, at this stage there is an increase in the tidal volume, and again the same problem, it decreases the assistance because it's a paradox. So at the end of the day, volume support also behaves with its limitations because it actually doesn't really support the patient and the effort actually goes up. What about PAV? PAV is very exciting. It's a mode called as proportional assist ventilation. Very exciting mode. It is like a power steering and a gentler form of pressure support. This is what PAV is all about. Alright. And for that, the equation of motion that Madam talked about is so important, where the total pressure or the work that is used is equal to the resistance plus elastance. Now the resistance is equal to resistance into flow. When you say P resistance is resistance into flow, and the elastance is elastance into volume. This is your equation of motion. Now let's take the example. Okay, let's take an example of how we are going to use the equation of motion. On the yellow you have the airway, and the blue you have the elastance. So let's take the airway resistance to be 5 centimeters of water. Let's look at the elastance at 10 centimeters. Okay, and the end expiratory lung volume is 2500 ml. Right? Now what I'm going to do, I'm going to initiate a breath. I'm going to give a tidal volume of 500 ml. And when I give a tidal volume of 500 ml, I fix the flow at 60 liters per minute. That means a liter per second. Alright, and the alveoli is going to expand. So it goes from 2500 to 3000. That means 500 ml has been delivered. At the same time, now I'm going to calculate whatever is happening over here. So the resistance goes on top, it's 5. Okay, the flow over here is 1 because it's a liter per second. I go to the elastance, which I had already talked about as 10. It's not going to change. Okay, and the volume I know it's 500, isn't it? It's 0.5 liters. Once I put into this, I now know my P total. And now I can program the ventilator to give a proportion of the P total, thus working as a support to this patient during ventilation. That's about proportional assist ventilation in short. So PAV measures the flow and volume instantaneously. At every instant it measures the flow and the volume. That's how it actually figures out the P total. Alright, and then it measures every 4 to 10 breaths by using a 300 millisecond pause. And then it determines the P total. And then the clinician sets the support that it wants to set, say a 40% or a 50% of the P total. And that's how proportional assist ventilation works. A little bit confusing, you might think that is very similar to pressure support, but it's not. Let me explain to you. Let's take this graph. Okay, this is a patient that is moving from different phases of his ventilation. So let's take the pre-muscle. Okay, so it's going from top to down, and all the time the muscular effort is changing for this patient. Sometimes it's high, sometimes it's low. So this is the way it actually moves throughout during the phase of ventilation. The pressure support, if you deliver at 8 or say 10 or you fix it up, it's always going to be pressure support the same. Muscular support will be different. Actually, the P muscle is very different. So the PS will remain the same. But what we really want is not something like this. What we want is, as the P mass changes, the proportion that I'm going to help should change. And this is exactly how I want it. And this is exactly what proportional assist ventilation does. It changes the work proportionately to the amount of effort that the patient is making. In short, it matches what we want to do and makes the patient very, very comfortable. Well, then we come to APRV, and I think probably this is something that I learned so much in COVID, and I think probably one of the best modes I've ever worked with, in my opinion. But there is, frankly, it should not be thought that it's the best mode or something like that. It's the best mode that I like to work with. Okay, so there is no best mode per se. So what do we do when there is hypoxia? I think you'll be talking about hypoxia in some time, isn't it? All right. So what do we do when there is hypoxia? A few things that we do, we increase the airway pressures. Okay, the second thing we do is increase PEEP. Alright. The third thing we do, we make an inverse ratio. Alright. The fourth thing is perform a recruitment. We paralyze the patient. Okay, and then we probe. Now these are the things that we do regularly when we have a patient with hypoxia. I don't have ECMO in my hospital, so I don't go to that extent. So what does APRV do? So APRV is actually a mode where a patient can breathe at a higher pressure and breathe at a lower pressure. This is what exactly APRV is all about. Now let's go to understand what it is. So that's the high pressure, that is the low pressure, and that's the time on the x-axis. Alright. So this is the inspiration that we are talking about, or we call it as high, the time at which the patient is at high, and that is the time at which the patient is at low. Time at which the patient is at high pressure, and time at which the patient is at low pressure. Alright, and he's able to breathe on all these pressures. That's the real point of the story. But let's go back to our same graph. Okay, what does it do? It actually increases the airway pressure. Look at this. If it was going to be a ratio where it's going to be just here and then up, down, the blackness would actually be reduced. And more the blackness, more the airway pressure. So you have increased peak airway pressure and you have increased PEEP. Something that I love for hypoxia. The other thing is, you see, this is the inspiration and this is the expiration. What has it done? It's actually reversed it. So it's made the inverse. The APRV has actually made that inverse. And then the next step comes is, why should I recruit when the potential benefits are less? That's the big question that is always asked. And that's because of a large amount of problems with recruitment. The problems are a lot. It is a sudden elevation of pressure and is not sustained. It may cause harm. It needs to be repeated again and again. And there are no endpoints, etc., etc. A lot of things are there in recruitment. What does this do? It actually performs recruitment extremely gently, sustained, without any problem. And that's the reason that making recruitment gently is what APRV does. Alright? Another thing, we don't want to paralyze our patients. Remember this. We paralyze a patient goes into critical illness, coronary myopathy, patient goes home and cannot even catch a remote control and switch on the TV. This is what occurs in these patients. Okay? We don't want to paralyze these patients. And what does APRV do? It allows them to breathe without any problem at both pressures, and you don't need to paralyze your patients at all. So in short, I feel APRV is something that works beautifully well, especially during COVID. And then comes adaptive support ventilation. Now I think this is like the king. This is like the king of physiological closed loop control. Is exactly what we started with by saying we need to look at the physiology and we need to alter the settings. And this is exactly what adaptive support ventilation is all about. You just dial an ideal, you look at the ideal body weight, and then with the ideal body weight, you dial a minute ventilation. Once you dial a percentage of the minute ventilation, for example, if it's, I define that minute ventilation, it takes 3 test breaths, and then it calculates the inspiration, the total and the time of inspiration. From the patient, it takes the compliance and the resistance. From the patient, it takes the compliance and the resistance. It looks at spontaneous activity and calculates something called as REX, that is the time constant, expiratory time constant, and from patient breath by breath, and then determines what is the target respiratory rate and tidal volume that you should give to reduce the work of breathing. And then it adjusts the mandatory rate and inspiratory pressure. I mean, it does everything that we want it to do. This is what closed loop control is, and I think that is why this is the king of physiological closed loop ventilation. For example, let us take a target minute ventilation of 6.6 liters per minute. Alright. So on the x-axis you have the rate, and on the y-axis you have the volumes. So you have a whole range where you can keep it at 6.6. For example, right there on top, over there it can be somewhere there. The optimal is somewhere around 400 or tidal volume 424 or something, and the RR is 16. This is the optimal. Now what does the ventilator do? The ventilator actually looks at this graph and then figures out a place where there would be dead space ventilation. It figures out another space where there is going to be barotrauma and volutrauma. And then it again figures a space that will cause auto PEEP. And then tries to keep this patient in this small box. In this small box. All the time during ventilation, this patient is in the safe zone of ventilation, and this box that is there is the safe zone of ventilation. This is adaptive support ventilation. I think this is the future of physiological closed loop control. Well, this is the real PCLC that we talked about. What is the evidence? See, the evidence for all of these things, I'll have to take another talk for it. Okay, so it's not possible for me to take the evidence for this, but let me tell you out of experience that it's been great working with these modes. And any sufficiently advanced technology is actually indistinguishable from magic, I feel. It's amazing to actually see all these things. And yes, you can see all these lectures on my website. Thank you very much. And there is a book that I have written, which I would like to keep it in the library of anesthesia. This is a book that I have written, and you can take it from Amazon whenever you want, 5 years ago. Thank you, madam.
Sanjith. You really spoke very well, and it was an excellent, amazing lecture. Really great day. And those who are attending workshop obviously will have a further experience with it.
Thank you so much, sir, for this brilliant lecture and taking out time from a busy schedule to share your knowledge with us. I would like to call Dr. Ashwati to present sir with a token of appreciation. Huge round of applause, please. We'll now take a short tea break. I request you all to assemble here back in 20 minutes so they can